Howdy, and thanks for the opportunity to speak with you. My name is Andy Dessler, and I'm going to be talking today about climate models and why you should believe them. So let's begin by talking about what a scientific model is. So a scientific model is a mathematical representation of some real phenomenon, usually expressed in computer code. Now, it's important to realize that all models are approximations. They never contain every single physical process that you can imagine. So the challenge when you're building a model is to include the most important factors for whatever problem you happen to be investigating. So how do we actually build a climate model? Well, the first thing to realize is that the atmosphere is a fluid. So we're going to take a statistical mechanics view of this, and we're going to try to simulate homogeneous chunks of the atmosphere. In other words, we break the atmosphere up into boxes. This is referred to as the model's grid. And the size of these boxes is determined by how much computer power you have. Over time, as computers have gotten much more powerful, the grid simulated by these models has gotten much finer. Typically, modern models have grids that are about 100 kilometers by 100 kilometers in latitude and longitude, by 1 kilometer in altitude. So this is a three-dimensional grid that covers the planet and goes up in altitude. The boxes interact in such a way that the atmosphere conserves energy, mass, and momentum. So it obeys the laws of physics. And it includes other processes that we think are important. Solar and infrared radiation, for example, cloud physics, all of the things that we think matter for the climate are included. And just to give you an idea of the importance of the size of the grid, this is a weather map, and you can see that the size of the features of a weather map are 1,000 kilometers. So you can see there's a cold front in the middle of the US. There's a high pressure system of the Gulf of Mexico. There's a low pressure system in Canada. And these features are all about 1,000 kilometers across, what we call in the weather biz synoptic scale. And by breaking the atmosphere up into 100-kilometer boxes that are much smaller than these synoptic scales, it means that the model resolution is sufficient to resolve the large-scale atmospheric flow. And that means that we can simulate this from first principles. We can put into the model F equals ma and all the other laws of physics, and the model will generate realistic looking weather. You can take a climate model and you can look at it, and it does look like the weather on our planet. It does a pretty good job of this. And that's, again, because the model grid is sufficient to resolve the features in the atmosphere. Now, that's not true for everything, though. So let me give you another example. So here you see Florida, and you can see that with 100 by 100 kilometer grid box, there's maybe a dozen or two boxes over Florida. Now, let me put up an image from GOES satellite that shows clouds. And what we can see is the clouds are not uniform on length scales equal to the grid boxes. Within a grid box, the clouds can change significantly. So we can't simulate those from first principles because our grid is too big. Our grid's 100 kilometers by 100 kilometers, so it can't resolve individual clouds. So instead, we rely on something called parameterizations to handle these features that are much smaller than the size of the grid. And the way parameterizations work is they take quantities that the model can predict. So things like temperature or water vapor that are well predicted by the model because the grid is sufficient to resolve them. And it creates an empirical relationship between these quantities that we can simulate and the quantity that we need to that it can't specifically resolve, in this case, clouds. So if we want to predict cloud fraction, we want to write it as a function of the things that we can simulate, like temperature and water vapor. And it's an empirical relationship, and it needs to be tuned. So I've written here that the cloud fraction is some constant C times water vapor over temperature. I just made that up. But the key thing is the constant C needs to be tuned. You do that iteratively by running the model, and you change it until the model kind of looks like the real atmosphere. You get about the right cloud cover. So just to review, climate models contain all of the important physics that we think is regulating our climate. And people are always adding new things as they come up, and we kind of realize, oh, this process might be important. So models are always improving. They're always becoming more sophisticated. Large scale phenomenon, things like the weather pattern, can be simulated from first principles. You just put F equals ma into your model and the rotation of the earth and sunlight and those things, and voila, you get weather that looks right. And these things are very robust, and we can expect that the model will do a good job on those. Things that are small scale, clouds is the classic example, rainfall is another one. Those need to be parameterized. And those are the most uncertain parts of the model. So if the model is going to fail, it's probably going to fail because of a parameterization. Now, I've talked about the atmosphere, but models also have to include the ocean and the cryosphere and the biosphere. Now, not all models contain all of these, but at this point, the most sophisticated models contain essentially just about everything we can think is going on the planet that can affect the climate. And unlike what you might hear, these models have actually been extensively tested. The people who create the models, they spend a lot of time testing the models. This is what I've spent a lot of my career doing, testing models. So let me give you a few examples of the kind of tests that we put the models through. So this is a paper where the authors compared some runs that were done several decades ago to the observations since the models were run. And so the top panel shows temperature against time. The models were run in the late 1980s, and the blue line shows observations, whereas the black line shows the models. And the top panel shows that the models over-predicted the temperature by a bit. So you might conclude, well, models are running hot. But in fact, in order to get the prediction right, you not only have to have a model correctly simulate the climate system, but you also have to correctly predict how much carbon dioxide and other greenhouse gases were added to the atmosphere. And these model runs, the three black lines, all had too much greenhouse gases in them. If you adjust for that, you find that the models actually do an excellent job. That's what the bottom plot shows. I'm not going to go into the details of that, but you can ask me questions about that if you're interested. But overall, this comparison shows that the models are doing really well. And just to support that, this is another paper that came out recently that also looked at old predictions. So they looked at a temperature prediction from the late 1980s of what the pattern of warming would look like. That's the top plot. And the bottom plot is what the actual observations are. And you can see there's a lot of agreement on this. The models get the pattern right. So they get more warming in the Arctic than the Antarctic. They get more warming over land than ocean. They do the things that we expect them to do. And, you know, these two comparisons, while not unexpected, give us confidence that the models really understand something fundamentally right about the atmosphere. So let me talk about something which might be a little bit harder to get right, and that's precipitation. So rainfall comes from clouds. Clouds are not directly simulated by the climate. So rainfall has to be parameterized. And you could easily imagine that the models would do a terrible job of this. And so we want to test it. Now, one of the most important and long-standing predictions of climate models is that heavy rain is going to get more frequent and light rain will get less frequent. So heavy events like Hurricane Harvey, et cetera, are going to happen more often. And so we can actually look at observations to see this. And indeed, we can see this in these observations. So let me just tell you what this plot shows. The x-axis is percentiles. So on the left-hand side is the 90th percentile. And on the right-hand side is the 99.9th percentile. And the y-axis is the percent change in frequency between two observational periods, the middle of the 20th century and the end of the 20th century. And you can see that these heavy precipitation events are getting much more frequent. The heaviest precipitation events, the 99.9th percentile, is 45% more frequent at the end of the 20th century than in the middle of the 20th century. So indeed, this verifies the predictions of climate models. And we can compare these quantitatively on these two plots. The plot on the left is the same one I just showed. The plot on the right shows several model ensembles. And I won't go into what these are, but you can ask me if you have questions. And you see these have the same shape. And if anything, the models are under predicting how much precipitation is going to change. So, that's quite worrisome. So where do models fit in? Because one of the things I want to make sure is clear is climate science is not just climate models. There are people that actually believe that's the case, and that is absolutely not the case. So even though I've talked about climate models in this talk, I want you to be clear that climate models are just one part of the evidence we use to understand climate change. And the two most important parts are simple physical theories. Like, for example, we understand why if you add a gas that absorbs infrared radiation, a greenhouse gas, you'll warm the climate. That's simple physics, sophomore level physics. In addition, observations. We see the climate warming. We see ice melting. We see sea level rising. We see all of these things happening in the observations. And climate models are important because they take the simple physical theories, they allow us to integrate them in ways that you could never do without a computer. And then they allow us to make these quantitative predictions that we can then test against observations. So climate models are a key part of the problem, but by no means are they the only or even the main part of climate science. The main part of climate science is the physics and the simple physical theories that explain most of what we see. So let me summarize the way I always end all my talks with what do we know? So a very simple summary of climate science is it's real, it's us, it's bad, scientists agree, but we can fix it. I really like to emphasize the last thing. We have the technology to solve this problem. The reason we're not doing it is because we lack political will. At any rate, I thank you for your attention. I hope I have an opportunity to answer some questions. Thanks.